Okay, then
let's do it.
Hello, everyone. Welcome back to the Colchin seminar in differential algebra. And this afternoon or this morning, depending on your time zone, we are very happy to have Camilo Sanabria from the University de los Andes, who will speak on linear differential equations with algebraic solutions.
All right. So thank you very much, Daniel, and everybody for this invitation. It's been a while. I haven't been in this seminar, so I was very happy to receive this invitation. So that being said, let me just dive in. So this is a very classical subject. What is it about? So let's say you have so this is no fancy differential Galois theory, nothing. It's the classical Picard-Vessieux situation. So you have a finite group, and just to keep things tame around, I'm going to assume that it's primitive, so it cannot be decomposed. In particular, it's not in primitive, but very important that it's finite. So if you're given a differential, an LOD, linear ordinary differential equation with these coefficients, coefficients that are rational functions with complex coefficients. And this finite group that we fixed as differential Galois group, the question is how to write down the solutions. Yeah, how to present them. So this kind of irreducible LODs, irreducible because the group is primitive, I'm going to call them algebraic LODs. Yeah, since the differential Galois group is finite, all the solutions are algebraic. Therefore, I could legitimately call them algebraic LODs. So let me give you some history just so that we're all in the same page on this problem. So there is a very classical result from Klein that tells you that in the case where n equals 2, so you have a second order equation, the algebraic solutions can be presented in this way. What I mean by this way, it's here you can see the solution has three elements. First, there is a hypergeometric function. The argument in this hypergeometric function is s of t, so that's a rational function. And in front of it, you have f of t, which is a function that the logarithmic derivative is a rational function. So that's written right here. So, and that's how you can build up all these solutions to algebraic LODs of second order. Now, these hypergeometric functions that are parameterized with three parameters, alpha, beta, and gamma, those three parameters correspond to Schwarz spherical triangles. So let me give you a little bit an insight into how this goes. So let me draw here the sphere. So the Riemann sphere you have here. Let's say I have three singularities. Let's say this is infinity. Here you have 1, and here you have 0, but it can be with any amount of singularities that you can draw this diagram. It's just so that we have a sufficiently general situation, but without being overblowing. And I'm going to take half the sphere, an hemisphere. So here I take a point. I take a neighborhood of it in here. I can define a solution. So I'm going to call those two solutions y1 of z and y2 of z. I'm going to take the ratio of these two values. So that's going to be a point in the projective line in P1. And my Schwarz map is going to be this map. Z is sent to this. So where I'm going with all this, I'm going back to the sphere. So I have here back the sphere. And now what I'm gonna have is that all this hemisphere with the part behind also included there is gonna be sent to, well, you know, here there are no singularities, so nothing really new happens. But with these three singularities, the angles here, those flat angles, these pi angles, 180 degrees, are going to be bent. So this is going to be sent to a triangle. Yeah, here I have the image of infinity, here the image of 1, and here the image of 0, or however the order has to be so that it keeps the orientation. And the image is going to be here, a triangle. Yep. So basically afterwards, the Galois group, in this case, because the solutions are algebraic, the Galois group coincides with the monodromy. Therefore, I can act in here with the monodromy. In here is here up. So here I have P1. Here again, I have P1. I'm acting here up with the monodromy. So this is just going to be Mobius transformations. So it's a linear combination of a ratio of linear combinations. And I'm going to have a projection, yeah, after I act upon. And I'm going to be back here in the Riemann sphere. So I can compose these two maps. So this map here up, we're going to put capital S, is the Schwarz map. That's what he did. And here you have the projection. And here this composition is going to be small s. Okay? Now, what did Klein did? He realized that for this covering that you have here, in this covering, the sections of it are given by this Schwarz map of some hypergeometric functions or hypergeometric equation, and you take two of those solutions. And what you're going to get in here, so the sections of this map are going to be given by hypergeometric functions or Schwarz map associated to hypergeometric equations. And any other situation where you have LOD with algebraic solutions, well, it's going to be a pullback of this situation. So when this is an isomorphism or a degree 1 map, so what you're having here, this Schwarz map, it's a section. And in any other situation, well, it's going to be a pullback of this situation given by this S. Okay? So that's how you come up with this result. So that was basically the insight of Klein. Please, if there are any questions, like if the diagram is incomplete or whatever, you please interrupt me and ask me. So this is what I write down here, like y1 and y2 are two linearly independent solutions of the equation that the Schwarz map defines a tessellation of the sphere. So this is how—
I have a small question if I can. Sorry.
Yes, of course.
Could you go back to the previous slide?
The previous slide, all right.
Yeah,
Here.
This one. I'm just wondering if I'm missing something. The factor of a little f of t in front of the hypergeometric.
Yes.
Is there any reason to have that not just be like the nth root of a rational function?
Oh, yes. Yes. So let's see first why these things come up. In this diagram, I'm drawing here that your image is in P1. The image is, let's say it's invariant if I multiply both functions by a same function, yes? Because at the end is the ratio, and that's going to cancel, okay? And that function that is going to be required there is f, is that f that is in front. And the reason you can think about that is that when you construct the projective line, you start with a two-dimensional space, and you're identifying all the points in the same line. So what you're doing there to get the f is gauging that function with an equation on a line bundle. Yeah. So that line bundle is what you use to take exactly which point of the space you want to define your element in P1. I mean, at the very end, P1, I repeat, is a two-dimensional space where you're acting by multiplication, and then you obtain a one-dimensional space. That multiplication happens in a single ray, and that ray is a line bundle. And the differential equation that rules which point in that line bundle that you are going to obtain is a equation of it's of dimension one. It's a how to say it's a connection or an equation of order one. Yes, and therefore that's why you have this result that is simply a first order LOD. Yeah, I don't know if that is that satisfactory as an answer or.
Sure, I would have to think about it, and I don't want to take you away from your main story. I just mean that when you write down the right-hand side looks to me like it can only possibly be algebraic if this little f is actually an nth root of something. But
yes,
let's maybe shelve that for now, and we can come back to it if there's time.
Yes, but basically, yes. I mean, the solutions are algebraic, so everything that is happening here is algebraic. Yeah, if you take there, maybe that was the answer that you wanted, something more clear. Since everything is algebraic, if you multiply by something that is not an nth root but exponential of something, you lose the algebraicity. Okay. So, anyways, all right. So here is the image without the 3D situation. Now, when you take the monodromy, what is going to happen? You make a loop, and then you are in the other hemisphere of the sphere, and therefore you have another triangle. And when you close the loop, you come back to the same hemisphere, and you have another triangle. And in that way, you end up here with a continuation. You end up, this hemisphere is another triangle, and so on. And so on. And since the monodromy is finite, you're going to go back to the same situation. And well, this is the situation you obtain. Okay, these are drawings taken from this book, beautiful book by Yoshida, Hypergeometric Functions, My Love. And the Galois coverings, because at the very end, this covering that you have here on the right-hand side, given by pi of g, it's a Galois covering. So they're very well known, and they correspond either to a dihedral group that is 2, 2n, so it corresponds to this tessellation that you have in the upper left corner. And then you have the other groups, A4, S4, and A5. You know, they have icosahedral, tetrahedral, and the decahedral groups. And well, these are the situations you obtain. Okay? So this result was exploited by these three guys, Berkenbos, Van Hoye, and Jacques Arthur to turn it into an algorithm. Yeah, so first of all, they choose some favorite alpha, beta, and gamma. So these are, so you have alpha, beta, gamma for each of these possible Galois coverings of the sphere by the sphere. And so what are these? Are hypergeometric functions, so that when you take their Schwartz map, what you're going to get is, what you're going to get here is sections of this covering. There are plenty of possible choices, so they just took these ones. And they came up with ways to compute ST and FT very quickly, right? And that's what happens in Maple. Here I have, wait, somewhere I must have Maple. Here. So here I have, this is a very famous equation, Picard. I don't know if you can see, let me make this bigger. So when you ask Maple Kovacic's algorithm, he gives you this, and here, this corresponds to the S of t, that is here down, this is S, and the function f is this thing in front, okay? And here you recognize the alpha, beta, and gamma chosen so that you obtain that. One of those sections with the Schwarz map. But if you ask Maple to identify, to do this solve, so to solve generically, I mean, he's going to give you this. It's going to be another presentation of the solution. And here what you can see is that the choices are not unique, yeah, for the alpha, beta, and gamma. And particularly, this is not going to give you always the most simple. It's going to work, but it's not going to give you necessarily the most simple. And well, all these functions are related with the so-called Kummer quadratic. They're here. I was checking the name right before. Wait, if I could find it. Right before coming here. Yeah, the quadratic transformations are here. Also, Gauss identities. So you have plenty of identities in between these different hypergeometric functions. So you cannot really expect that with a single hypergeometric function, you're going to always have the easiest presentation. But anyway, the point here, so I don't deviate, is that this result of Klein, it's been algorithmically implemented. And it's useful, actually. Why it's useful? The original algorithm that gave rise to all these ideas of computing solutions efficiently, or at least Liouvillean solutions efficiently, is Kovacic's algorithm. For algebraic LODs, he didn't present the solutions in the same way as Klein suggested using hypergeometric functions, but as exponentials of antiderivative of algebraic functions. And what Kovacic did in his algorithm was to compute the minimal polynomial for this omega that is in the exponent. And well, the degree of those polynomials is not so big. You have 4, 6, 12, or 2, depending on whether you have A4, S4, A5, or the dihedral group. And what I understand, or what they told me back when I was in New York, was that when the algorithms show up first in '86 with the computers they had, they weren't able to compute this 12th order polynomial. And these kind of limitations still exist for other degrees, and I'm going to show you. Okay, so in that sense, using Klein's result is more efficient because computing these minimal polynomials was quite complicated. Now, there is another way of presenting these algebraic solutions, a rather obvious way, which I'm not saying that it's obvious to get the information required to compute, but a more natural presentation is to compute sincerely the minimal polynomial of y of t. So this is a work of Singer and Ulmer. They tell you that you can compute the minimal polynomial, not of the exponent omega, but of y, of the solutions y, and you have to pay a price. Yeah, so here the degrees were 4, 6, 12, and 2, and the price you pay to not using the exponential is, well, the minimal polynomials become big. Yeah, 24, go 120, can even reach, so that's horrible. And but you can do it, or at least theoretically, you can do it. No, nowadays we can do it. It's not so complicated. All right, so that's what I want to say about order 2. So you have 3 ways of presenting it using hypergeometric functions. In modern slang, you say the solution is projectively equivalent. So if I go back here, you say projectively equivalent to the pullback by a rational map of a hypergeometric function. So projective equivalent is because of this F. The pullback by a rational function is this S of t, and well, the hypergeometric function is rather obvious. So that's method 1. Method 2 is Kovacic algorithm, exponential of the antiderivative of an algebraic function. And method 3 is the classical, you just give the minimal polynomial of a solution. All right. Now, we move to degree 3. So you basically have the same 3 possibilities. Now you have the same presentation, but instead of taking hypergeometric functions, you have this sub G because it's what Berkenbos call standard equation, okay? The idea is exactly the same. So what are you gonna do? Basically, what is the idea here? What you're gonna do is you have the same situation here, but instead of having 2 solutions, you're gonna have 3 solutions. So let me change what has to be changed. So here you have y3. This is not gonna live anymore in P1, but it's gonna be in P2. And what you're gonna obtain here, it's a algebraic curve inside P2. So it can be as rich as you want. So for example, let's say a genus 3 surface, that you're going to obtain here. And this hemisphere is going to be sent into a triangle here up. And again, you can act with the monodromy and you're going to go back to P1, but this time you don't have a covering of the sphere by the sphere, but by any curve of the sphere. Yeah, you have a covering of the sphere by any curve, right? So, but basically it's the same situation, right? And what I mean by the same situation, what are these standard equations, so-called standard equations? Those are the equations so that when you take the Schwarz map, you're going to take sections of this covering. I don't know how you feel about all this, but for me, it's rather entertaining because generally when you see a course in algebraic topology, you have all these coverings and all that, and you have a lot of hand waving with the sections, but these elements are actually giving you the precise algebraic functions that you need to build up these sections of these coverings, right? And so this is what's going on. The standard equations are the ones that give you exactly the coverings, and any other situation, let's say given a curve, if you find another equation so that the associated Schwarz map is a parametrization of the same curve, maybe it's going once, twice, thrice over that curve, well, you know that that setting is a pullback of this setting where the Schwarz map is giving you sections, and that pullback is going to be given by if you go over 5 times over this curve, well, this thing is going to be of degree 5, okay? So that is the idea, again. So it's just basically going one more dimension, and that's what Berkenbos did. A problem from an algorithmic perspective is that there are infinitely many standard equations for each group. It's not like before that for each group you can pick one, your favorite standard equation, hypergeometric equation, but for every group you have infinitely many. So this is kind of a issue for the, plus you don't even have a structure. With Berkenbos result, you don't have any structure about those standard equations. So from an algorithmic perspective, this is an issue. Yeah, I mean, theoretically, it's very nice, but algorithmically, you cannot implement it because you have infinite amount of standard equations. Now, Van Heu, Rago, Ulmer, and Weil, they generalize Kovacic's result to order 3. So there you go, exactly the same way of presenting the solutions Kovacic style. And now, what are the degrees of the minimum polynomial of that omega in the integral of the exponent? Well, are these. So you have degree 6 or 15, depending where you have A5 cross C3, the cyclic group, or 45 or 21 or 9, if you have these subgroups down, are the subgroups of the hashing groups. This G168 is the Klein simple group. A6 is Valentiner group. That thing has order huge. It's like 1080 or something like that. It's 360 times 3. So let you do the math. Exactly. Yeah, 1080. They're big groups. You can also do the same thing in the same paper, Singer and Ulmer compute the minimal polynomial, and you can see that degrees are getting completely out of hand. Now 36 times 6. That's rather big, 108. I think. I don't know. Anyways, the important thing is that the order is way more than 108. I went up there with the computations. But they're big. Yeah, it's the same idea. You pay a price, yes, to get these minimal polynomials. So more recent history. Well, of course, I generalized this result to any order. So it's just for any n, not 2, 3. This is the same behavior for all the n's. And the idea is exactly the same. So if you want to make a diagram here, what you're going to leave is in Pn plus 1, here, around here. It's going to be changed, but besides that, it's exactly the same idea. And what is the geometry of the problem? What is the geometry of the problem? Well, I pretty much gave you the geometry, but let's try to make it more algorithmically. You have a primitive group. You have a basis of solutions. You have the Schwarz map. This Schwarz map, the image, is what was called the Fano curve. This is important. This was what Gino Fano back in the 19th century studied. That's why it's called Fano curve. And if the Galois group is finite, it coincides with the monodromy, and the monodromy acts on this Fano curve. Yeah, so the group defines an action on this X Fano curve, and we obtain a covering. That's what was in the right-hand side of my drawings. Now, if the Schwarz map is a section of the covering, we say that the equation is standard of this covering of the sphere by the Fano curve. The result is that if two Schwarz maps describe the same Fano curve up to a projective transformation, then the two equations, you have two equations, and the two equations define the same Fano curve. Then the two equations are projectively equivalent to the pullback by a rational function of the same standard equation. Yeah, they're just pullbacks of the same situation. And the standard equations are in correspondence with rational curves of this quotient. Yes, at the very end, like if we go back here, you can take this G group not acting on this curve, but on P2. And what you're going to obtain is that, well, for every rational curve in this quotient here, when you take, let's say, P2C modeled by G, if you take a rational curve down here, well, you can unwind all this and bring you back to this situation. Yes, of course, you take the pre-image up, you're going to have a covering, then a Gaussian covering of the sphere by the curve, whatever you obtain your own. So that gives you kind of some characterization of all these LODs with finite algebraic group, which when you think deeply about it is rather obvious. All right, so let me show you pretty much how you make all this. All this is just a corollary, how you prove these theorems, how you come up with these results. These are corollaries of Compoint's theorem from '98. So what Compoint's theorem tells you in the algebraic case is more general for the reductive case, but I'm here giving you a watered down version. So what you take your evaluative isomorphism, you call x1 till xn your generic, just variables, generic functions, and you're going to evaluate them with the solutions to your equation. Yeah. And obviously this is a CT algebra morphism. Sorry, I call here T the variable Z, but it's because I like to think of this as parametrizing curves. So parametrization time, that's why I use T. So this evaluation morphism has a kernel I. The Galois correspondence is telling you that here there should be x's. Yes, these y's are wrong. It should be x. If you take a G invariant polynomial, then the value is going to be a rational function, that's the Galois correspondence. You take generators of your invariant algebra. So finitely many, because at the very end we're having a finite group, but in the reductive case you also have finite of them generators. And because of the Galois correspondence, the image is going to be a rational function fi, and so the difference between this invariant polynomial and the value fi are going to be in the kernel. And Galois, what Compoint's theorem is telling you is that those generate the invariants, the kernel. So basically what it's telling you is that all the information of the LOD, or at least all the information that the Galois theory can extract from an LOD, is synthesized by these solutions down, these equations down, sorry. That's all the information. And what you can do is from this information here, build up the equation. Actually, you can do it algorithmically. I have a paper on that, and here's the algorithm. So it's not so long, but algorithmically, these are the invariants that I have here. So here are the invariants for degree 2. For A5, here you have the values to give you the rational function in the quotient. And, well, I don't know if I can run this live. What you're going to do is extract the solution. You take enough derivative, and there you go, you obtain the equation. Yeah, so you take implicit differentiation, you differentiate enough times, you take linear relations in between those, the equations you obtain by differentiating this, and that's going to give you the coefficients, and you do some Grobner basis tricks, and you get the coefficients. All right, but the point is that this information is the equations down are giving you all the information, and from there on you can obtain everything. Now, let me give you some examples about all this. So here we have Klein simple group of order 168. It's generated by these 3 guys. It's not really important who are they. It's just important that they are available in the literature. These are the invariants. So here up you have the polynomial that when you equal 0, you obtain Klein's quartic. You take the Hessian of this F4, yeah, and you obtain a 3×3 matrix. You take the determinant. So when you differentiate twice, you lose 2 degrees. So it's 2 of each entry. So 2 times 2 plus 2 plus 2 is 6. So you get a 6th order polynomial. All right, you have 2 invariants, F4 and F6. Now, if I take the border Hessian, so you do that when you are computing optimization with the Lagrangians. So you obtain here in the upper right corner of this new matrix the Hessian, and in the border you have the gradient of F6. You take the determinant of this, you get another invariant F4. Now, G168 is acting on a 3-dimensional space. You take F4, F6, and F14, which are invariant polynomials that you can use as a coordinate system of this orbit space. And, well, so the Jacobian of this projection that you're going to take from C3 into the orbit space using F4, F6, F14, it's a new matrix that is down. So you take the Jacobian of these 3 functions, and you're going to get the final invariant 21. You have 4 invariants. The 4 invariants are going to have an algebraic relation between them, and that's so-called syzygies. This is the syzygy. All right. So this is just the structure of the invariants. So whenever I have rational functions in this orbit space, I can produce LOD with algebraic solutions, that the Galois group is going to be G168. So there is this classical equation of Hurwitz from 1886. So you roll up your sleeves and compute the invariance of the Galois group. So you have F4 equals 0. So this is a parametrization of Klein's quartic. And that's the reason why Hurwitz came out with this equation, was to parametrize Klein's quartic, which is just this F4 equals 0. Yeah. And this is genus 3. You compute the other invariants, F6, F14. So are those. So what is this telling me? Now I'm going to see if I'm getting a standard equation or not. So I'm going to take a rational function on the orbit space. So that's a ratio of two homogeneous polynomials of same order. So here, what I do is bring order 42. So that's 6 to the 7th and 14 to the 3rd times 3 and 6 times 7. So I raise this polynomial value to the 7th power for F6 and to the 3rd power for 14. Take the ratio and I divide by this cube number 1728, and you obtain T. What is this telling you at the very end? It's telling you that this here, S, is a degree 1 function, and this is basically an isomorphism, this arrow down, small s, it's an isomorphism, it's actually just T. Yeah, and what you're having here is that the Schwarz map of these two solutions of Hurwitz equations are sections of a covering of the Klein quartic covering the sphere. Okay, so what the results are promising, that if I have any other equation that is parametrizing Klein's quartic, I should be able to compute the its solutions using solutions of this Hurwitz equation. Now, for algorithmic purposes, this Hurwitz equation is not the best. Here on the side, this, if you do this map and you go up to the universal covering, what you're gonna get is this psychedelic image. So this is a covering of the, you're not gonna have any more spheres, and these things are high genus, so you are in the hyperbolic space. So this is the same situation of the images of Yoshida, but now in hyperbolic space. And so as I was saying, this equation is not good because these values are horrible. The value of F6 and the value of F14 are horrible. What I would really like is to multiply the solutions very much how you take the degree 2, the degree 1 coefficient that you multiply, you do a projective equivalence. I can do a projective equivalence here and make so that the value of F6 is going to be 1. Yeah, so this is a Hurwitz equation. These are the values. And I'm going to take another equation. This is a 3F2 equation that also parameterizes the Klein quartic, but it has the benefit that the value of the 6th order invariant is going to be 1 instead of this horrible polynomial here that I have of degree 7 in the denominator. Rational function with degree 7 polynomial in the denominator. So how I'm going to use this to produce a solution. So let me show you. You go around and find an equation that parameterizes Klein's quartic. So there is in this paper of Van der Put and Unwer for the year 2000, this another equation. So you compute the invariance. What do you obtain? F4 is 0, so you checked it parameterizes Klein's quartic. F6 is not 1, is this 27 divided by t to the 4 times t minus 1 to the 5th power. And the ratio of degree 42 invariance that give you t before is going to give you now this polynomial of degree of this rational function that defines a function of degree 4. So what are you going to do? This f6 that Carlos was asking about at the beginning is going to be the 6th root of this 27 divided by something. And the st is going to be this other rational function that is completely down of degree 4. Yeah, so, sorry. So you carve up your solution. How? Taking the 6th root, that's what is in front, and the parameter in front is going to be that value s of t. Okay, so that's how these results work. Now you take other curves, so the Hessian of Klein's quartic, so you find it, you have another somewhere, you have now, it's not f4 but f6 that has value 0. You can make it so that the value of f4 is 1, so now you have a 3f2 equation. And again, you find another equation that parameterizes, this is wrong. Well, I put here the wrong slide, but there is another equation that parameterizes the Hessian of Klein's quartic. And you can make the same recipe, but instead of using the ratio of, well, the ratio of two degree 42 functions is different. This one doesn't have 1,728 in the denominator, but 256, and so on. But the problem is that not all the invariant curves are the Hessian of Klein's quartic or Klein's quartic. So, sorry, I put some wrong slides. So what about other parametric curves? What are we gonna do? So this is the solution I suggest. You have a new curve, let's say that's the red curve, and you have your favorite curve, which should be f4 equals 0. We are just talking about equations that have got a group G168, all right? For other groups, we need another geometry, but this is just an example, what we do. And so the black curve down is gonna be f4 equals 0, Klein's quartic. So I take a point in the curve I'm working with, or yes, the curve parameterized by the Schwartz map of the LOD you're working with, and you draw a tangent. That tangent is going to hit f4 somewhere. So you call that time it takes to hit the tangent f1 of t0. This is a question you can put in vector calculus to your students, provided you have parameterizations of these curves. And for another point, f1 is different. Yeah. And so let's apply that to another equation. This is one more equation in van der Put and Ulmer. The values of the invariants are these. So you know f4 is not 0, f6 is not 0. So what are we going to do? Here you have a proof. This is the equation of the curve. So I want to compute this f1 of t. Because if I have f1, I know that this linear combination, which is actually a gauge equivalent, which is in the left-hand side, is a gauge transformation of the original equation. I'm going to obtain something that I can compute in terms of that hypergeometric function I used to compute the solution to anything that is parameterizing Klein's quartic. So I roll up my sleeves, I compute these guys. So I get this f1, I compute everything. So now I have a gauge equivalent equation to my original equation that can be expressed in terms of the functions for the Klein's quartic. I can write that down in matrix form, but what I want is to express y1 in terms of the other functions I know. So I just invert this matrix, and what I get is y1 in terms of as a gauge transformation of the other functions I know. And well, this has been algorithmically implemented. But I'm already running out of time. Let me show you the code. So here is the code, and it's rather lengthy, and here is that example. So I don't know if he's going to finish, but this is the time it takes to compute the Galois group. And after I'm going to come back because it takes like some seconds and I have very few time to do it. But these are just to show you that this can be done algorithmically. So what about other groups? These are all the groups. I'm going to wrap up. I don't know how long more I have. I should have finished already, isn't it?
We started a bit late, so you have a few minutes. That's okay.
You're very kind, Daniel. I see like Alexei nodding. Yeah, you should have already be done, man. Take it easy, Alexei. You can always disconnect. No, anyways, here are the groups. And so these are the possible groups. So now you have to find favorite equations. Where you get them? Well, in the literature. This is something done by Cato. Let me go back here. Oh, here's the solution. Yeah, all right. So here you got it back. Anyway, it's not so pleasant to see. It's a rather lengthy formula, but it's okay. And anyways, who cares? So for the other groups, you need to find equations that parameterize your favorite curves. So here there's a whole bunch of equations that parameterize different curves. These are the favorite curves. So you should take the favorite because they have the least order. So on top is times quartic, and after you have here for A5, after you have for, let me see, this is A6, and on the bottom you have for H216 and F36. And well, you have other nice diagrams. This is G168. For A6, you have this covering. For H216, the Hessian curve, you have this. And for F36, this is my favorite because it's a elliptic curve, so it's flat geometry. So actually, it's not something hypergeometric nor spherical. And well, I mean, I don't know. Let's say that you can do this for other orders with the same geometry. And at the very end, you have the same kind of result. And the take-home message is that given a finite primitive group of any dimension, one can choose a standard equation so that the solution to every LOD with differential Galois group, that group you choose G, can be expressed in this form. Yeah, so you pick the standard equation and then the rest of them can be expressed in terms of that one. And well, that's it. Look, after their tricks, there is a lot of algebra there. This algorithm is going to show up now in ISAC conference, and the algorithm is joint work with Thierry Combo. And pretty much this is the algorithm. Yeah, but given the amount of time that I have, which is null, I don't have time to go over. But that's it. I mean, that's kind of what I wanted to present to you guys.
Okay, thank you very much for your very nice talk.
Thank you.
Are there questions from the audience? Please just unmute yourself or write in a chat.
I'm going to go back to this image because it's nice to finish with.
Yeah.
Anyways.
Inspiring.
very inspiring, or yeah, if not psychedelic. Yeah.
Well, I was just wondering at the end with your algorithm with Thierry, what you presented in the examples, there were a couple of steps where you relied on, let's say, knowledge of certain parametrizations of curves, like you know, the Klein quartic curve, and you already knew that F32 would be useful, etc., right?
Yes.
And so in the algorithm at the end,
yes,
this was more general, right? You have to incorporate a few things to be able to treat the old examples that way, or
like, let's say that what you have to do is carefully check every group and choose a nice curve that you want for that group. Yes, and then any other equation, you're going to try to make some transformation in it so that at the end, you're going to end up parametrizing that favorite curve that you chose.
Okay, so that was a way to get a convenient expression anyway.
Exactly.
Right? Yeah.
Exactly.
Okay, yeah.
And let's say that there is a work to be done. Like you have to be acquainted enough with the geometry of that specific group so that you get an equation that parameterizes that curve that you chose. Yeah, so we all the time, and let's say that that's hard coded in the algorithm. Yeah. So for example, here, like you see, basically, when I solve the primitive case, what you're doing is passing those parameters that you want for each of those curves. So this is the data group G168. You use the same one here and here. Yeah, but for other groups, you need to identify, like here, let's say here for H72, you need to identify exactly which 3F2 equation you need for that.
Yeah, yeah.
Let's say that you know that. I mean, it's part of the algorithm, and if you want to generalize this for degree 4, 5, or whatever, you will need to come up with this n-1 equation that will give you that curve. Yeah.
Thank you. Are there other questions?
Well, not being any. Yeah. All right. Sorry.
Please go ahead.
Not really a question, Camilo. Very, very nice talk. But will you make your slides available on the website?
Yes, of course. Of course. Actually, I came to realize that just checking before that you don't have the proper address of my web page. So because there is one generic that is given by the institution, but so this is my other one, and here you can find the Maple code. Yeah, here it is. Sorry, it's in Spanish, but it's kind of not so friendly. So the code is there, and of course I'm going to give to the I'm going to share the slides, and I don't know where they're going to post them, if they're going to post them, or I can send it to you directly if you want to see them.
Usually we collect them also on the Colchin Seminar webpage. So
perfect.
Whenever you have a version of your slides that you think is publishable in that sense,
all right,
then we are very happy to put this up.
Perfect. I'll try to. I'll get the correct slide here for this other example that was misplaced. Yeah. So once I do that, hopefully I'll do it in the next few hours. But if not during this weekend, and I'll send it. So it's going to be available soon. But I'll send them to you directly, Andy, if that's okay with you. Well, no. However, they're going to be in the seminar webpage.
Thank you for this. Other questions or comments? Well, if this is not the case, then thank you all for attending and participating. This is the last session for this semester. There will be no session next week, so we will be very happy to welcome everyone back in the fall semester for a new edition. And have a good afternoon or rest of the semester.
Right. Well, thank you, and happy summer for everybody.
Thank you. Bye-bye.
Bye. Bye.
Bye.
Bye, everyone.